Our story begins not on Mars but here, on Earth, in a quiet moment. Perhaps you're looking up at the night sky, or perhaps you're simply wondering, as humans have always wondered, about what lies beyond. There is something in the human spirit, something ancient and persistent that refuses to accept boundaries. We are a species of explorers, of dreamers, of those who stand at the edge of the known world and ask, what lies beyond? This is not merely curiosity. It is something deeper. It is a fundamental part of what makes us human. Tonight, somewhere on Earth, a child looks up at a reddish point of light in the evening sky and asks, "What is that?" An adult answers, "That is Mars." The child asks, "Can we go there?" And in that simple question lies the entire arc of human ambition, the entire trajectory of our species. For thousands of years, Mars has beckoned to us, a rusty beacon in the darkness, close enough to see clearly, yet impossibly far away. It has been a god, a mystery, a destination, and perhaps someday a home. But before we can understand whether Mars can truly be our future home, we must first understand what home means. What makes Earth our home? Is it simply the place where we were born, the planet that happened to give rise to life? Or is home something deeper, something that can be recreated, something that can be carried with us across the vast emptiness of space? These are not merely practical questions about engineering and survival. They are profound questions about identity, about what it means to be human, about whether the human story is forever bound to one small blue world, or whether it is a story that can be written across multiple worlds, multiple skies, multiple horizons. Let us begin this journey not with rockets and mathematics, but with the most human of emotions, longing. The longing to explore, to discover, to push beyond our current boundaries. This longing is not new. It is as old as humanity itself. Our distant ancestors standing on the shores of Africa looked across the waters and wondered what lay beyond. They built boats from reeds and logs, fragile vessels that should not have worked, and they sailed into the unknown. They crossed oceans without maps, guided only by stars, by currents, by an inexplicable faith that there was something worth finding on the other side. They populated every continent, adapted to every climate, from frozen tundras to scorching deserts. Humans are, by nature, migrants. We are a species that moves. For most of human history, this migration happened on foot, or by boat, or on the backs of animals. The scale was planetary, but it was comprehensible. A person could walk from one side of a continent to another, and while it might take months or years, it could be done. The world was large, but it was finite and traversable. The horizon always held the promise of new land, new resources, new possibilities, but then something changed. We reached the edges. We mapped the entire planet. We crossed every ocean, climbed every mountain, explored every desert. The era of terrestrial exploration came to an end, not because we lost our curiosity, but because we ran out of places to go. The map was complete. Every point of land had a name, a flag, a claim. The world suddenly felt smaller, more crowded, more finite, and yet the longing did not disappear. If anything, it intensified. We turned our gaze upward. If there are no more new lands on Earth, then perhaps there are new lands beyond Earth. Perhaps the next frontier is not horizontal but vertical. Perhaps home is not a single planet, but a concept that can be extended to other worlds. This is where Mars enters our story. Mars is the next shore, the next horizon. It is close enough to reach with our current technology, or at least with technology we can envision. It is a real place, not a fantasy, not a mathematical abstraction, but a world of rock and ice and dust that we can see with our own eyes. It is a world that might, just possibly, become a second home. But before we set sail for this new shore, we must understand what we are leaving behind, and what we hope to find. We must understand Earth, our first home, in all its complexity and beauty. Only then can we truly appreciate what it would mean to make another world our home. Let us pause here, in this quiet moment of longing, and reflect on the blue planet beneath our feet. Let us appreciate its air, its water, its life. Let us feel the gravity that holds us to its surface, the atmosphere that protects us from radiation, the biosphere that feeds us. Earth is not just a planet. It is a system, a delicate and intricate web of interactions that has taken billions of years to evolve. It is the only known place in the universe where life exists. It is, in the most literal sense, irreplaceable. And yet, we dream of Mars. Why? Is it simply because we can? Because it is there? Or is there something deeper, something more essential driving this dream? Perhaps it is the recognition that Earth, for all its beauty, is fragile, that life on a single planet is vulnerable, that a single asteroid, a single supervolcanic eruption, a single self-inflicted catastrophe could end the entire human story. Perhaps Mars represents not just adventure, but insurance, not just exploration, but survival. Or perhaps the reason is even simpler, even more profound. Perhaps we look to Mars because we are human, and humans explore. It is what we do. It is who we are. The longing to see what lies beyond the next hill, the next ocean, the next sky, is not a choice. It is our nature. As we stand here, looking up at that reddish point of light, we are continuing a story that began hundreds of thousands of years ago. We are the descendants of those who wondered what lay beyond. We carry their curiosity in our genes, their courage in our dreams. The journey to Mars is not a departure from the human story, it is its continuation. With this understanding, with this sense of continuity and purpose, we are ready to begin our journey. We are ready to ask the questions that will guide us. What is Mars? Can we reach it? Can we survive there? Can we truly make it our home? And most importantly, what does it mean for us as a species to take this next great step? The answers will require us to journey through science and engineering, through biology and psychology, through economics and ethics. But most of all, they will require us to journey through our own imaginations, to envision a future that does not yet exist, to see ourselves not just as inhabitants of Earth, but as a species capable of inhabiting worlds. Our journey to Mars begins now, not with a rocket launch, but with a single profound question. What is home, and can it be found among the stars? Chapter 2. The Red Neighbour, Understanding Mars. Before we can dream of making Mars our home, we must first understand what Mars actually is. Not the Mars of mythology or science fiction, but the real Mars, the planet that orbits our sun, the world of stone and ice that waits in the cold darkness of space. Understanding Mars requires us to see it not as a destination, but as a world with its own history, its own character, its own story that has been unfolding for billions of years. Mars is our neighbour. In the vast scale of the solar system, it is remarkably close. When the orbits align favourably, Mars and Earth can be separated by as little as 34 million miles, or about 55 million kilometres. This sounds like an enormous distance, and it is, by terrestrial standards. But in cosmic terms, it is practically next door. Light, travelling at 186,000 miles per second, takes only about 3 minutes to cross this gap. A radio signal from Mars reaches Earth in the same time. In the context of a solar system where distances are measured in billions of miles, Mars is our closest potentially habitable neighbour. But proximity alone does not make Mars similar to Earth. In fact, Mars is a study in contrasts, a world that is at once tantalizingly familiar and utterly alien. Let us begin with the basics, the fundamental physical characteristics that define Mars as a world. Mars is smaller than Earth, roughly half the diameter and about 1/10 the mass. If you could place the two planets side by side, Earth would look like a large blue marble, while Mars would be a smaller rusty red ball. This difference in size has profound implications. A smaller planet means weaker gravity, only about 38% of Earth's gravity. On Mars, if you weigh 100 pounds on Earth, you would weigh only 38 pounds. This might sound liberating, and in some ways it is. You could jump higher, lift heavier objects, move with an ease that would be impossible on Earth. But this same weak gravity is also the source of many of Mars's greatest challenges. Gravity is not just what keeps your feet on the ground, it is also what holds a planet's atmosphere in place. Earth's strong gravity creates a thick atmospheric blanket, a protective shield that keeps our air from escaping into space, that moderates temperature, that shields us from harmful radiation. Mars, with its weak gravity, has lost most of its atmosphere over billions of years. What remains is a thin whisper of gas, mostly carbon dioxide, with a surface pressure only about 0.6% that of Earth's. To put this in perspective, the atmospheric pressure on Mars is roughly equivalent to the pressure at an altitude of 100,000 feet above Earth's surface, far higher than any airplane flies, in the realm of near vacuum. This thin atmosphere has dramatic consequences. Without a thick atmospheric blanket, Mars is exposed to the full fury of space. Cosmic rays and solar radiation bombard the surface unimpeded. Temperature swings are extreme. On a sunny day at the equator, the temperature might reach a relatively pleasant 70 degrees or 20 degrees, but at night, without an atmosphere to trap heat, temperatures can plummet to 100 degrees or 73 degrees. The average temperature on Mars is about 80 degrees or 60 degrees, far colder than Earth's most inhospitable regions. The thin atmosphere also means there is virtually no weather as we know it. There are no rain showers on Mars, no thunderstorms, no gentle morning mists. Water cannot exist as a liquid on the surface because the atmospheric pressure is too low. Any water would either freeze or instantly evaporate. And yet Mars does have weather of a sort. It has winds, sometimes fierce winds, that whip across the plains and valleys. It has dust storms that can, on rare occasions, engulf the entire planet, turning the sky a murky brown and blocking out the sun for months. These dust storms are a reminder that Mars, while cold and dry, is not dead. It is a dynamic world, still shaped by forces of nature. The surface of Mars is a landscape of extremes and contradictions. In many ways, it resembles the deserts of Earth, vast expanses of red sand and rock stretching to distant horizons. The colour, that distinctive rusty red that gives Mars its name, comes from iron oxide, essentially rust, that covers much of the planet's surface. Mars is a world that has oxidized, a world that has, in a sense, corroded over billions of years. But Mars is not just a featureless desert. It has mountains, and not just any mountains. Olympus Mons, the largest volcano in the solar system, rises 69,000 feet above the surrounding plains, nearly 3 times the height of Mount Everest. It is a shield volcano, built up over millions of years by countless lava flows, a monument to a time when Mars was geologically active, when its interior was hot enough to drive volcanic activity on a truly planetary scale. Mars has canyons, and again, not just any canyons. Valles Marineris, the Great Rift Valley of Mars, stretches for over 2,500 miles, roughly the distance from New York to Los Angeles. It is up to 125 miles wide in places and plunges to depths of 23,000 feet. If placed on Earth, it would span from coast to coast across the United States. This is a geological feature of such immense scale that it defies easy comparison. It is a scar on the face of Mars, a testament to ancient tectonic forces that once shaped the planet. Mars has polar ice caps, visible even through a small telescope from Earth. These caps are made of both water ice and frozen carbon dioxide, dry ice. They grow and shrink with the Martian seasons, expanding in winter and receding in summer. The water ice is particularly significant because water, in any form, is essential for life as we know it. The presence of water ice on Mars, both at the poles and beneath the surface in many regions, is one of the key reasons we consider Mars a potential home. And Mars has channels, ancient riverbeds, dried lake beds, and what appear to be the remnants of ancient shorelines. These features tell a story of a very different Mars, a Mars that once had liquid water on its surface, a Mars that was warmer, wetter, and perhaps more hospitable to life. This ancient Mars is one of the great mysteries of planetary science, and understanding what happened to it is crucial to understanding whether Mars can become a home again. The current theory, supported by a wealth of evidence from orbiting spacecraft and surface rovers, is that Mars was once much more Earth-like. Billions of years ago, perhaps 3.5 to 4 billion years ago, Mars had a thicker atmosphere, liquid water on its surface, and possibly even oceans. But Mars is a small planet, and small planets cool faster. Over time, Mars's core cooled and solidified. Without a molten core, Mars lost its magnetic field. Earth's magnetic field, generated by the churning of molten iron in its core, acts as a protective shield, deflecting the solar wind, a stream of charged particles constantly flowing from the sun. Mars, without this protection, was vulnerable. The solar wind stripped away its atmosphere over millions of years, molecule by molecule. As the atmosphere thinned, the pressure dropped, the water evaporated or froze, and Mars transformed from a potentially habitable world into the cold, dry desert we see today. This is the Mars we face, the Mars we hope to make our home. It is a world with a tragic history, a world that once had promise but lost it. It is a world that is, by any Earth standard, hostile to life. There is no breathable air, no liquid water, no protection from radiation, no warmth. It is a world where stepping outside without a spacesuit would result in death within seconds. Your blood would boil, not from heat, but from the low pressure. You would suffocate, not from lack of oxygen, but from the inability of your lungs to function in a near vacuum. You would freeze, exposed to temperatures that would make Antarctica seem tropical. And yet, we look at this world and we see potential. We see a world that is close, that has resources, that has a day roughly similar to Earth's, that has gravity strong enough to walk on, that has water, even if it's frozen. We see a world that is, despite all its challenges, the most Earth-like planet in our solar system. We see a world that, with enough ingenuity, enough technology, and enough determination, might be transformed. But before we can talk about transformation, about terraforming, about making Mars green and blue and alive, we must first talk about something more immediate, more practical, more essential. We must talk about how to simply survive there. We must understand the challenges, the dangers, the obstacles that stand between us and a sustainable human presence on Mars. We must be realistic, clear-eyed, and honest about what we're facing. The dream of Mars as a home is beautiful and inspiring, but dreams must be grounded in reality. And the reality of Mars is harsh, unforgiving, and demanding. To make Mars our home will require us to solve problems that have never been solved before, to develop technologies that do not yet exist, to push the boundaries of human knowledge and capability further than we have ever pushed them. It will require sacrifice, risk, and an unwavering commitment to a goal that will take generations to achieve. As we stand here, contemplating this red neighbour, this cold and distant world, we must ask ourselves, are we ready? Do we have the knowledge, the technology, the resources, and most importantly, the will to take this step? The answer, we will discover, is complex. It is both yes and no. We are closer than we have ever been, but we are not there yet. The journey to Mars is not just a journey through space. It is a journey through time, through innovation, through the very limits of what humanity can achieve. With this sobering and yet exciting understanding, we are ready to move forward. We are ready to explore not just what Mars is, but how we might reach it, survive on it, and perhaps, someday, truly call it home. Chapter 3. The Journey, Crossing the Void. The distance between dreaming of Mars and standing on Mars is not just measured in miles, but in engineering challenges of almost incomprehensible difficulty. To reach Mars, we must first escape Earth, then traverse tens of millions of miles of empty space, then slow down enough to enter orbit or land on the surface without burning up or crashing. Every step of this journey pushes the limits of our technology and tests the limits of human endurance. Let us begin with the most fundamental challenge. Leaving Earth, Earth's gravity is strong. To escape it, to reach orbital velocity, a spacecraft must accelerate to about 17,500 miles per hour, or roughly 28,000 kilometers per hour. This is fast enough to circle the Earth in about 90 minutes. To escape Earth's gravity entirely, to embark on an interplanetary journey, requires even more speed, about 25,000 miles per hour or 40,000 kilometers per hour. Achieving this speed requires enormous energy, and the only practical way we currently have to generate this energy is through chemical rockets. A rocket is, at its core, a beautifully simple machine. It works on Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket expels gas out of its engine at very high speed in one direction, and the rocket moves in the opposite direction. The faster the gas is expelled, and the more gas is expelled, the more thrust the rocket generates. But here is the fundamental problem. To carry enough fuel to reach high speeds, you need a large rocket. But a large rocket is heavy, which means you need even more fuel to lift that weight. But more fuel makes the rocket heavier still, requiring even more fuel. This is known as the tyranny of the rocket equation, and it means that the vast majority of a rocket's mass at launch is fuel, not payload. A typical rocket to Mars might be 95% fuel by weight. This means that only 5% of the rocket's mass is the spacecraft itself, the cargo, the crew, and all the supplies needed for the journey. This is why rockets are so enormous. why they require such complex engineering, why they are so expensive. Every kilogram of payload to Mars requires hundreds of kilograms of fuel to get it there. Even with our most advanced rockets, the journey to Mars takes time. Unlike a flight across an ocean where you can simply point your aircraft in the right direction and fly, space travel requires careful planning and precise timing. Planets orbit the Sun at different speeds and at different distances. Earth orbits closer to the Sun than Mars and therefore travels faster. To reach Mars, we cannot simply aim for where Mars is now and fly straight there. By the time we arrive, Mars will have moved. We must aim for where Mars will be, and we must time our launch to take advantage of the orbital mechanics. The most efficient way to travel to Mars is to use what is called a Hohmann transfer orbit, a path that takes advantage of the relative motion of the planets. This opportunity, when Earth and Mars are in the right positions relative to each other, occurs only once every 26 months. This is known as a launch window. Miss the window, and you must wait more than 2 years for the next one. During a favourable launch window, the journey to Mars takes between 6 and 9 months, depending on the exact trajectory and the power of the rocket. 9 months. That is roughly the same amount of time as a human pregnancy, a reminder that the journey to Mars is not a quick trip but a long, difficult and dangerous voyage. And during those months, the astronauts would be confined to a small spacecraft, travelling through the void of space, millions of miles from any help, any rescue, any return. The psychological and physical challenges of such a journey are immense. The spacecraft would be cramped, the routine monotonous, the isolation complete. There is no fresh air, no fresh food, no sunlight, no gravity. Everything must be brought along or recycled. Water, air, food, all must be carefully managed. A single failure of a critical system could be catastrophic. The absence of gravity is both a blessing and a curse. In zero gravity, objects are weightless, which makes moving large items easier and allows for fascinating experiments. But the human body did not evolve for zero gravity. Our bones, muscles, and cardiovascular systems are designed to work against Earth's gravity. In zero gravity, bones lose density, muscles atrophy, the heart weakens, and fluids shift toward the head, causing a puffy face and potential vision problems. Astronauts on the International Space Station, who spend only months in zero gravity, must exercise for hours every day to counteract these effects. Even with rigorous exercise, they still experience significant bone and muscle loss. On a journey to Mars, astronauts would spend 6 to 9 months in zero gravity, then face the challenge of adapting to Mars's gravity upon arrival, then potentially spend months or years on Mars before making the return journey through zero gravity again. The long-term health effects of such exposure are still not fully understood. Radiation is another serious concern. Earth's magnetic field and atmosphere protect us from most cosmic radiation and solar radiation. In space, there is no such protection. Astronauts on a Mars mission would be exposed to levels of radiation far higher than anything experienced on Earth or even on the International Space Station, which still benefits from some protection from Earth's magnetic field. High-energy cosmic rays can penetrate the hull of a spacecraft and damage DNA, increasing the risk of cancer, cataracts, and other health problems. A single large solar flare, a burst of radiation from the Sun, could deliver a lethal dose of radiation to unprotected astronauts. Spacecraft must be designed with shielding, but shielding adds weight, which makes the rocket problem even more difficult. Finding the right balance between protection and practicality is one of the many engineering challenges. And then there is the simple fact of the distance. If something goes wrong on the journey to Mars, there is no quick rescue. If a fire breaks out, if a system fails, if someone becomes seriously ill, the crew must handle it themselves. Communication with Earth, even at the speed of light, takes between 3 and 22 minutes one way, depending on the distance between the planets. This means a conversation with mission control involves delays of 6 to 44 minutes between question and answer. Real-time guidance is impossible. The crew must be highly trained, resourceful, and capable of making critical decisions independently. Despite all these challenges, the journey to Mars is not impossible. It is difficult, yes. It is risky, absolutely. But it is within the realm of what we can achieve with current or near future technology. Multiple space agencies and private companies are actively working on Mars mission plans. NASA's Artemis program aims to return humans to the Moon as a stepping stone to Mars. SpaceX is developing the Starship, a fully reusable spacecraft designed explicitly for Mars missions. China, Europe, India, and other nations have their own Mars exploration programs. The pieces are being assembled, the technology is being developed, the knowledge is being gained. But let us not underestimate the magnitude of the undertaking. Sending humans to Mars will be one of the greatest achievements in human history, a feat of engineering, courage, and cooperation on a scale rarely seen. It will require the combined efforts of thousands of scientists, engineers, technicians, and astronauts. It will require billions of dollars in funding sustained over many years. It will require political will, public support, and a shared vision of the future. And it will require accepting risk. The journey to Mars will be dangerous. There will be setbacks. There may be tragedies. But if history is any guide, if we are true to our nature as explorers, these challenges will not stop us. They will inspire us to work harder, to be smarter, to be better. Imagine for a moment the experience of that journey. Imagine sitting in a spacecraft looking out a small window at the Earth shrinking behind you, becoming a blue dot, then a point of light, then disappearing entirely into the blackness. Imagine the silence of space, the endless void, the stars that do not twinkle, because there is no atmosphere to distort their light. Imagine the slow passage of days and weeks, the routines of life in a cramped metal tube, the camaraderie and occasional tensions of a small crew isolated from the rest of humanity. Imagine the moment when Mars begins to grow from a point of light to a disk, to a world, its rusty surface becoming visible, its features becoming clear. Imagine the mixture of excitement and terror as the spacecraft approaches, as the engines fire to slow down, as the moment of landing approaches. This is the reality of the journey to Mars. It is not a glamorous adventure from a movie. It is a difficult, uncomfortable, and sometimes terrifying experience that will test every limit of human endurance and ingenuity. But it is also potentially the most profound human experience imaginable. The experience of becoming the first to set foot on another world, the experience of extending the human presence beyond the cradle of Earth. And if the journey is this challenging, what of the destination? What will it be like to actually live on Mars, to survive in such a hostile environment? The journey is only the beginning. The real test comes when the spacecraft lands, the airlock opens, and human beings step out onto the red sands of an alien world. The real question is not just can we reach Mars, but can we stay? Chapter 4. Arrival. First steps on an alien world. The moment of landing on Mars would be one of the most significant moments in human history, a moment that would echo through time, a moment comparable to the first humans stepping out of Africa, or the first humans landing on the moon. But unlike those moments which represented exploration and discovery, landing on Mars would represent something more, the intention to stay, to build, to establish a permanent human presence on another world. Let us imagine that moment. The spacecraft has been travelling for months. The crew is exhausted both physically and mentally. But as Mars grows larger in the windows, as the moment of arrival approaches, exhaustion gives way to adrenaline, to focus, to a mixture of excitement and terror. The spacecraft enters Mars's thin atmosphere at enormous speed, experiencing heat and deceleration forces that strain every component. Parachutes deploy to slow the descent. Retro rockets fire to cushion the final touchdown. And then, silence. The engines shut down. The spacecraft rests on the surface. For a moment, no one moves. They simply sit, breathing, processing the fact that they have arrived, that they are alive, that they are on Mars. The first view out the window would be surreal. The landscape would be familiar and alien at the same time. The surface would be red and rocky, dotted with boulders and dunes, stretching to a distant horizon. The sky would be a strange colour, not the blue of Earth, but a butterscotch hue, a consequence of the thin atmosphere and the dust suspended in it. The sun would look smaller, about 2/3 the size it appears from Earth, because Mars is farther from the sun. The light would be dimmer, a perpetual late afternoon glow, even at midday. And then, the moment of first contact with the surface. The crew would don their spacesuits, bulky and cumbersome, but absolutely essential. Without a spacesuit, a human would survive on Mars for only seconds. The suits must provide air, pressure, temperature regulation, and protection from radiation. They are, in effect, miniature spacecraft wrapped around the body. The airlock would cycle, the pressure equalized, the outer door opened, and one person, chosen by whatever criteria the crew or mission control has decided, would step out first. The first step on Mars would feel different than a step on Earth. The gravity is weaker, about 38% of Earth's, so the person would feel lighter, bouncier. A gentle hop would carry them higher than they could jump on Earth. But the sensation would also be strange, unsettling, because the body's sense of balance, its proprioception, is calibrated for Earth's gravity. Moving would require relearning, adapting, adjusting. Simple tasks that are automatic on Earth would require conscious thought on Mars. The first footprint in the Martian dust would be crisp and clear, a mark that could last for centuries in the absence of wind and rain. It would be a symbol, a declaration. Humans were here. But it would also be a reminder of fragility, of how utterly dependent the astronauts are on their suits, their habitat, their life support systems. A single tear in a suit, a single malfunction, could be fatal. The first priority upon landing would not be exploration or science, but survival. The crew would need to establish a base, a habitat that can provide shelter, air, water, food, and warmth. This habitat would likely have been sent ahead on an unmanned mission, a prefabricated structure that the crew would need to activate, inspect, and make livable. The habitat would be their home, their fortress against the Martian environment. It would need to be airtight, pressurized, and equipped with systems to recycle air and water, to generate power, and to maintain a comfortable temperature. Life inside this habitat would be unlike anything on Earth. The crew would be confined to a relatively small space, perhaps a few interconnected modules, each the size of a small room. There would be no going outside without a spacesuit, no opening a window for fresh air, no stepping into a garden. Every resource would be limited and precious. Water would need to be recycled with extreme efficiency, processed and purified again and again. Air would need to be regenerated, with carbon dioxide removed and oxygen produced, likely through a combination of chemical processes and plants. Food would come from stored supplies brought from Earth, supplemented if possible by crops grown in a greenhouse. Waste, including human waste, would need to be carefully managed, potentially processed for use as fertilizer or even broken down for other resources. Power would be essential. On Mars, solar panels are a viable option, as the planet receives sunlight, though less intense than on Earth. However, dust storms can block the sun for weeks or months, reducing the effectiveness of solar power. Nuclear power, using small modular reactors, might be a more reliable option, though it adds complexity and risk. Without power, the habitat's life support systems would fail. Without power, the crew would freeze or suffocate. Power is not just a convenience on Mars, it is a matter of life and death. Communication with Earth would be a lifeline, but also a source of frustration. The time delay, ranging from minutes to tens of minutes depending on the planet's positions, would make real-time conversation impossible. Sending a message and receiving a response could take almost an hour at times. This delay would create a sense of isolation, a feeling of being truly alone on a distant world. The crew would need to develop a culture of independence, of self-reliance, of solving problems without waiting for instructions from Earth. The psychological challenges of living on Mars would be profound. The isolation, the confinement, the distance from loved ones, the constant awareness of danger, the monotony of routine, all would take a toll on mental health. Studies of people living in analogous environments such as Antarctic research stations or submarines show that psychological stress is one of the greatest challenges. Small annoyances can become major conflicts. Personality clashes can escalate. Depression, anxiety, and other mental health issues can emerge. Careful crew selection, ongoing psychological support, and strategies for maintaining morale and cohesion would be essential. And yet, there would also be moments of profound beauty and wonder. Imagine standing on the rim of Olympus Mons, the tallest mountain in the solar system, looking down at the plains thousands of feet below. Imagine watching a Martian sunset, the sun dipping below the horizon, the sky turning shades of pink and purple. Imagine seeing Earth as a bright evening star, a blue dot in the blackness, and knowing that everyone you have ever known, everyone you have ever loved, is on that tiny point of light. Imagine the sense of accomplishment, of pride, of being part of something larger than yourself, of being a pioneer, of making history. The early days, weeks, and months on Mars would be focused on establishing a foothold, on proving that humans can survive. The crew would conduct scientific experiments, explore the local area, test equipment, and gather data. But more importantly, they would be learning how to live on Mars, developing the skills and knowledge that would be essential for future missions, for long-term habitation, for transforming Mars from a destination into a home. But survival is not the same as thriving. Survival is about enduring, about not dying, about maintaining the minimum necessary conditions for life. Thriving is about more. It is about building, growing, creating, developing a society, a culture, a sense of place. To truly make Mars a home, we would need to move beyond survival to sustainability, to self-sufficiency, to a point where Mars is not just a base that depends entirely on Earth for supplies, but a world that can support itself. This transition from survival to sustainability is perhaps the greatest challenge of all. It would require developing new technologies, new industries, new ways of living that are adapted to Martian conditions. It would require using Martian resources, not just bringing everything from Earth. And this brings us to a concept that is both exciting and essential: in situ resource utilization, or ISRU. Chapter 5: Living off the Land, in situ resource utilization. The key to making Mars a sustainable home is to stop thinking of it as a destination that must be supplied from Earth and start thinking of it as a world with its own resources that can be used to support human life. This concept, known as in situ resource utilization, or ISRU, is the difference between a temporary outpost and a permanent settlement. It is the difference between dependence and independence. Earth is rich with resources. We have air to breathe, water to drink, materials to build with, energy, from the sun, fossil fuels, and renewable sources. Mars, at first glance, seems barren, but appearances can be deceiving. Mars does have resources. They are not as abundant or as easily accessible as Earth's, but they are there, and with the right technology, they can be used. Let us begin with the most essential resource: water. Water is life. It is needed for drinking, for growing food, for hygiene, for producing oxygen, for creating fuel. Without water, a permanent human presence on Mars is impossible. The good news is that Mars has water. It is not liquid, but it is there, frozen beneath the surface and at the polar ice caps. Radar instruments on orbiting spacecraft have detected vast amounts of subsurface ice, particularly at mid and high latitudes. In some regions, ice makes up a significant fraction of the soil, mixed with dirt and rock. This ice could be mined, extracted, and melted to produce liquid water. The process would not be simple. It would require machinery to dig, heat, and collect the water vapor, then condense it into liquid form. But it is technically feasible. The polar ice caps are another potential source. These caps contain large amounts of water ice, though they are also mixed with frozen carbon dioxide. Extracting water from the poles would require establishing operations in some of the coldest and most inhospitable regions of Mars, but it could provide a substantial water supply for a large settlement. Once we have water, we can do remarkable things with it. We can drink it, obviously, but we can also split it into hydrogen and oxygen through a process called electrolysis, which uses electricity to break the water molecule apart. The oxygen can be used for breathing. The hydrogen can be combined with carbon dioxide from the Martian atmosphere to create methane, which can be used as rocket fuel. This is significant. If we can produce fuel on Mars, we don't have to bring it from Earth. This makes return missions far more feasible and reduces the cost and complexity of Mars missions dramatically. A spacecraft traveling to Mars could carry only enough fuel to land, knowing that it could produce the fuel for the return journey on the Martian surface. The Martian atmosphere itself is a resource. It is thin, but it is there, and it is mostly carbon dioxide. Carbon dioxide can be used in multiple ways. It can be combined with hydrogen to create methane and water, as mentioned. It can be converted into carbon monoxide and oxygen through a process called solid oxide electrolysis. The oxygen, again, is useful for breathing and fuel. The carbon monoxide can be used in industrial processes. Even the nitrogen and argon present in small amounts in the atmosphere can be extracted and used. Martian soil, known as regolith, is another valuable resource. Regolith contains minerals, metals, and potentially useful chemicals. It could be processed to extract iron, aluminum, silicon, and other elements that could be used. for construction, manufacturing, and electronics. The regolith itself could be used as a building material. Bricks could be made by compressing regolith and baking it in a kiln, or by using the regolith as a component of concrete. Structures could be built using 3D printing technology, where a robotic printer lays down layers of processed regolith to create walls, habitats, and other structures. Building underground or covering habitats with regolith would also provide protection from radiation. Mars has no magnetic field and a very thin atmosphere, so the surface is exposed to high levels of cosmic radiation and solar radiation. This radiation is a serious health hazard for long-term habitation, but regolith is a good shield. A few meters of dirt or rock above a habitat would significantly reduce the radiation dose to safe levels. Future Martian settlements might look less like futuristic glass domes, and more like underground or partially buried structures, using the planet's own material as protection. Energy is another critical resource. Mars receives sunlight, though it is about 44% as intense as sunlight on Earth, because Mars is farther from the Sun. Solar panels can work on Mars, and in fact they have powered rovers and landers for years. However, solar power has limitations. Dust can accumulate on panels, reducing their efficiency. Dust storms can block the sun for extended periods. For a permanent settlement that needs reliable power year-round, solar power alone may not be sufficient. Nuclear power is an alternative. Small nuclear reactors, similar to those used on submarines or in remote locations on Earth, could provide a steady, reliable power supply regardless of weather or time of day. These reactors would need to be safe, compact, and designed for the Martian environment, but the technology exists and is being developed. A small nuclear reactor could power a habitat, life support systems, resource processing equipment, and scientific instruments. Another potential energy source is geothermal energy. While Mars is geologically less active than Earth today, there may still be regions with residual heat from ancient volcanic activity. If geothermal hotspots can be located, they could potentially be tapped for energy, though this remains speculative. The goal of ISRO is to create a closed-loop system where resources are used, recycled, and reused with minimal waste. Water would be recycled through life support systems, with losses made up from Martian ice. Air would be regenerated with oxygen produced from water or atmospheric carbon dioxide. Waste would be processed to extract useful materials or converted into fertilizer for growing food. Over time, as the technology improves and the settlement grows, the dependence on Earth would decrease. Eventually, a Martian settlement could become largely self-sufficient, producing its own food, water, air, fuel, building materials, and energy. This is the vision of sustainable Martian life. It is not easy. It requires advanced technology, significant upfront investment, and a willingness to innovate and adapt. But it is possible, and it is essential. Without ISRO, Mars will always be a costly, high-risk destination that depends on a constant flow of supplies from Earth. With ISRO, Mars can become a true second home, a place where humans can live, work, and thrive independently. But living sustainably is only part of the challenge. Humans need more than just air, water, and shelter. They need food. They need purpose. They need community. They need a reason to stay. This brings us to the question of agriculture, of growing food on an alien world, of creating a biosphere where none exists. Chapter 6. Growing Life. Agriculture on Mars. To make Mars truly habitable, to transform it from a place of survival to a place of living, we must be able to grow food. Bringing all food from Earth would be impractical and unsustainable for a long-term settlement. Food is heavy, it spoils, and it requires significant space and energy to store. A single person needs roughly 2,000 calories per day, which translates to about 1.5 to 2 pounds of food, depending on the type. For a crew of just 10 people, that's 20 pounds of food per day, or over 7,000 pounds per year. For a settlement of hundreds or thousands, the numbers become astronomical. The only practical solution is to grow food on Mars. But can plants grow on Mars? Can life, which evolved on Earth, adapted to Earth's atmosphere, Earth's gravity, Earth's soil, and Earth's sunlight, thrive in such a different environment? The answer is, potentially yes, but it will require careful engineering and adaptation. Plants need a few essential things to grow: light, water, carbon dioxide, nutrients, and a suitable temperature. Mars, surprisingly, can provide some of these. It has sunlight, though weaker than on Earth. It has water, frozen in the soil and at the poles. Its atmosphere is mostly carbon dioxide, which plants use for photosynthesis. What Mars lacks is a breathable atmosphere, stable temperatures, and rich soil. But these can be provided artificially in a controlled environment. The most practical approach to agriculture on Mars would be to use greenhouses, sealed structures where temperature, pressure, and atmosphere can be controlled. These greenhouses would be pressurized with a breathable mix of gases, likely with higher levels of carbon dioxide than Earth's atmosphere to maximize plant growth. They would be heated to maintain temperatures suitable for plant growth, probably in the range of 60 to 80 degrees Fahrenheit or 15 to 27 degrees Celsius. They would be illuminated by sunlight, possibly supplemented with artificial lighting, especially during dust storms or in regions with limited sunlight. The soil, or rather the growing medium, would be a challenge. Martian regolith is not soil in the Earth sense. It lacks organic matter, the decomposed plant and animal material that makes Earth soil fertile. It may contain perchlorates, toxic chemicals that would need to be removed before plants could grow safely. But regolith could be used as a base. It could be mixed with organic matter, such as composted human waste or plant waste, to create a viable growing medium. Nutrients such as nitrogen, phosphorus, and potassium would need to be added, either brought from Earth initially or eventually produced on Mars. Hydroponics and aeroponics, methods of growing plants without soil, could also be used. In hydroponics, plants grow with their roots submerged in a nutrient-rich water solution. In aeroponics, roots hang in the air and are misted with a nutrient solution. Both methods use less water than traditional soil-based agriculture and can be highly efficient, making them well suited for the resource-constrained environment of Mars. They also eliminate the problem of Martian regolith and allow for precise control over nutrient delivery. What crops would we grow? Not all plants are equally suited for a Martian greenhouse. We would prioritize crops that are nutritious, fast-growing, and efficient in terms of water and space. Likely candidates include potatoes, which are high in calories and relatively easy to grow. Potatoes have been proposed and even featured in popular culture as a staple Martian crop. They provide carbohydrates, vitamins, and some protein. Lettuce, spinach, and other leafy greens, which grow quickly, are nutrient-dense and can be harvested continuously. They are also well suited for hydroponic systems. Tomatoes, peppers, and other vegetables, which provide variety and important vitamins. Wheat or rice for staple grains, though these may be more challenging due to their longer growing cycles and higher resource requirements. Legumes, such as beans and peas, which are high in protein and can fix nitrogen in the soil, potentially reducing the need for nitrogen fertilizers. Algae and spirulina, which can be grown in bioreactors, are incredibly efficient at converting carbon dioxide and light into biomass, and are high in protein and other nutrients. They could serve as both a food source and a component of life support systems, helping to regenerate oxygen and remove carbon dioxide. The first Martian farms would be small, experimental, and heavily reliant on Earth for seeds, equipment, and knowledge. But over time, as the techniques are refined, as the systems become more efficient, and as the settlement grows, agriculture could expand. Eventually, a large enough greenhouse complex could produce enough food to feed the entire settlement, with surplus that could be stored or traded. But agriculture on Mars is not just about food production. It's also about creating a more Earth-like environment, a touch of green in a red desert, a reminder of home. Plants bring life, not just in a biological sense, but in a psychological sense. They purify the air, they provide oxygen, they create a sense of growth and renewal. For astronauts living in a confined, artificial habitat on a barren world, a greenhouse could be a sanctuary, a place of peace and beauty, a connection to the living Earth they left behind. Imagine walking into a Martian greenhouse. The air would be warm and humid, filled with the scent of growing plants, a stark contrast to the cold, dry, odourless atmosphere outside. The light would be soft and green, filtered through leaves. There would be the sound of water dripping, of ventilation fans humming softly. Rows of plants would stretch out, vibrant and alive, a testament to human ingenuity and the resilience of life. This small oasis of green in a world of red would be more than just a farm. It would be a symbol of hope, a sign that humans can not only survive on Mars, but can bring life with them. But even with successful agriculture, even with a self-sustaining food supply, there are deeper questions to consider. Can humans truly thrive on Mars long term? What are the biological, psychological, and social challenges of living on another world for years, decades, or even generations? This brings us to the human element, the most complex and unpredictable part of the Mars equation. Chapter 7. The Human Element, Bodies and Minds on Mars. Technology can solve many problems. We can build habitats, generate power, produce water, grow food. But technology alone cannot make Mars a home. Ultimately, the success of a Martian settlement depends on the humans who live there, on their ability to adapt, to endure, to maintain their health and sanity in an environment that is fundamentally alien. Let us first consider the physical challenges, the ways in which the Martian environment affects the human body. We have already discussed radiation, which is a serious concern. On Earth, we are protected by a magnetic field and a thick atmosphere. On Mars, there is no such protection. Astronauts would be exposed to cosmic rays and solar radiation at levels far higher than on Earth. Over time, this exposure increases the risk of cancer, cataracts, damage to the central nervous system, and other health problems. While habitats can be shielded with regolith, time spent outside in spacesuits, even with shielding in the suit, would still accumulate radiation dose. Medical advances such as better cancer screening and treatment, and possibly pharmaceutical interventions that protect cells from radiation damage would be essential. The low gravity of Mars, while making movement easier in some ways, poses its own challenges. We have seen the effects of zero gravity on astronauts on the International Space Station: bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems. Mars has gravity, but it is only 38% of Earth's. What are the long-term effects of living in such low gravity? We do not fully know, because no human has ever spent an extended period in partial gravity. It is possible that Mars's gravity is sufficient to prevent the worst effects of zero gravity. It is also possible that it is not, and that over years Martians would experience significant health issues. Exercise, diet, and possibly pharmaceutical interventions would likely be needed to maintain bone and muscle health. There is also the question of reproduction and child development. If humans are to truly settle Mars, if it is to become a home, children will eventually be born there. But can a human fetus develop normally in Martian gravity? Can a child grow up healthy in such low gravity, with their bones and muscles forming in an environment so different from Earth? Will children born on Mars ever be able to visit Earth? Or would Earth's stronger gravity be unbearable, even dangerous for them? These are profound questions with no current answers. They will only be answered by taking the risk, by attempting it, and this is one of the ethical dilemmas of Mars colonization. The psychological challenges are equally significant. Isolation, confinement, monotony, distance from loved ones, the constant awareness of danger, the inability to simply step outside and breathe fresh air. All of these factors would take a toll on mental health. Studies of people living in isolated, confined environments on Earth, such as Antarctic research stations, submarines, and space stations, provide some insight. These studies show that psychological stress is a major issue. Common problems include depression and anxiety, which can be triggered by isolation, lack of sunlight, and the monotony of routine. Interpersonal conflicts, which can arise from living in close quarters with the same small group of people for extended periods. Small annoyances can escalate into major disputes. Cabin fever, a general sense of restlessness and irritability that comes from being confined indoors. Sleep disturbances, which can be caused by the artificial lighting, the lack of natural day-night cycles, and stress. Cognitive decline, including problems with attention, memory, and decision-making, which can result from stress, sleep deprivation, and the monotony of the environment. Strategies to mitigate these psychological challenges would include careful crew selection, choosing individuals who are psychologically resilient, adaptable, and able to work well in a team. Ongoing psychological support, including access to counselors or therapists via communication with Earth, would be important. Maintaining a structured routine with regular sleep schedules, exercise, work tasks, and leisure time would help provide a sense of normalcy. Opportunities for privacy, for personal space, would be essential in a cramped habitat. Communication with family and friends on Earth, despite the time delays, would provide an emotional lifeline, and there would need to be opportunities for recreation, for activities that provide enjoyment and a break from work. This could include hobbies, games, movies, music, books, and social activities. A small library of entertainment media, a collection of books and films could provide a vital escape. Artistic endeavours such as painting, writing, or music could provide a creative outlet. Even simple activities, like cooking special meals on occasions or celebrating holidays and birthdays, could provide moments of joy and connection. But beyond the individual psychological challenges, there is a broader social question. What kind of society would develop on Mars? A Martian settlement would, by necessity, be highly cooperative and interdependent. Everyone would rely on everyone else for survival. Individualism, in the sense of I can do whatever I want, would be impossible. The needs of the group, the survival of the settlement, would have to take precedence. This could foster a strong sense of community and solidarity, a culture of mutual support and shared purpose. Or it could lead to authoritarianism, to rigid hierarchies, to a loss of personal freedom. The governance of a Martian settlement would be a complex issue. Initially, a small crew would likely be governed by mission protocols and directives from the sponsoring organisation on Earth, whether it is a government space agency or a private company. But as the settlement grows, as the population increases, as children are born and raised on Mars, the question of self-governance would arise. Would Mars remain a colony, dependent on and controlled by Earth, or would it seek autonomy, self-determination, perhaps even independence? These questions touch on issues of politics, law, ethics, and human rights. They are questions that humanity has grappled with throughout history in the context of terrestrial colonies, and they will arise again in the context of space colonization. There is also the question of culture. What would Martian culture be like? Would it be an extension of Earth culture, a transplanted version of American, Chinese, European, or other cultures? Or would it develop its own unique identity, shaped by the unique challenges and experiences of living on Mars? Language, art, music, traditions, values, all of these elements of culture would evolve in response to the Martian environment. Perhaps Martians would develop their own slang, their own music, their own stories and myths. Perhaps they would see themselves not as expatriates from Earth, but as Martians, as a new branch of humanity, adapted to a new world. And perhaps most profoundly, there is the question of meaning and purpose. Why would people choose to live on Mars? What would motivate them to leave Earth, to endure hardship, to risk their lives, to raise families in such a challenging environment? For the first pioneers, the answer might be adventure, the thrill of exploration, the desire to make history. But for a long-term, sustainable settlement, people would need deeper reasons. They would need to believe that life on Mars is worthwhile, that it offers something valuable, something meaningful that cannot be found on Earth. This could be the opportunity to be part of something larger than oneself, to contribute to the greatest human endeavour in history, to build a new world from scratch. It could be the appeal of a frontier society, with opportunities for those who are willing to work hard and take risks. It could be the satisfaction of living in a close-knit community, where everyone knows everyone, where cooperation is essential, where individual contributions are valued. It could be the philosophical appeal of living on Mars, of experiencing a fundamentally different relationship with the environment, of living sustainably, of appreciating the fragility and preciousness of life in a way that is difficult to grasp on abundant Earth. The human element is the most unpredictable, the most challenging, and ultimately the most important aspect of making Mars our home. Technology will get us there, science will tell us how to survive, but it is the human spirit, the human capacity for adaptation, cooperation, creativity, and resilience that will determine whether Mars becomes a true home or just a barren outpost. It is the human heart that will make Mars a place worth living. Chapter 8. Terraforming, Remaking a World. If we can survive on Mars, if we can establish a sustainable settlement, the next question is, can we transform Mars? Can we change its atmosphere, its climate, its entire environment to make it more Earth-like? This is the concept of terraforming, literally Earth-shaping, the process of engineering a planet to support human life without the need for habitats and spacesuits. Terraforming Mars is one of the most ambitious, audacious, and controversial ideas in all of science and philosophy. It is a project that would take centuries, cost unimaginable sums, and fundamentally alter a world. But it is also an idea that captures the imagination, that speaks to humanity's desire to control nature, to expand our domain, to make the universe our own. Let us be clear from the outset. Terraforming Mars is not something we could do today, or even in the near future. It is a long-term goal, a vision for what might be possible centuries from now if we develop the necessary technology, if we muster the will, and if we decide that it is ethically acceptable. But it is worth exploring because it forces us to think deeply about what it means to make a planet a home, about the limits of our power, and about our responsibilities. The goal of terraforming Mars would be to make its surface habitable without life support. This means creating an atmosphere that is thick enough to breathe, that provides adequate pressure, that protects from radiation, and that maintains temperatures warm enough for liquid water to exist on the surface. It means transforming Mars from a cold, dry desert into something resembling Earth, with oceans, rivers, perhaps even forests and grasslands. Is this even theoretically possible? The answer, according to current scientific understanding, is maybe. Mars has some of the ingredients needed for terraforming, but not all of them, and the process would be extraordinarily difficult. The first challenge is the atmosphere. Mars's current atmosphere is far too thin. To make Mars habitable, we would need to thicken the atmosphere significantly, increasing the pressure from the current 0.6% of Earth's pressure to at least 10 to 20% of Earth's pressure, and ideally closer to Earth's pressure. We would also need to change the composition. The current atmosphere is 95% carbon dioxide, which humans cannot breathe. We would need to add oxygen, nitrogen, and other gases to create a breathable mix. Where would all this gas come from? One idea is to release gases that are currently trapped on Mars. The polar ice caps contain frozen carbon dioxide. If we could warm Mars, this frozen CO2 would sublimate into gas, thickening the atmosphere. Mars's regolith may contain trapped water and carbon dioxide that could be released by heating the soil. Some proposals suggest using nuclear devices, orbital mirrors to focus sunlight, or factories that produce greenhouse gases to warm the planet and trigger the release of these trapped volatiles. This is called a runaway greenhouse effect, where warming leads to the release of gases, which causes more warming, which releases more gases, in a positive feedback loop. However, recent studies suggest that Mars may not have enough trapped volatiles to create an Earth-like atmosphere, even if we could release them all. The solar wind has been stripping Mars's atmosphere for billions of years, and much of it may be permanently lost to space. This is a significant problem. If Mars doesn't have the raw materials for a thick atmosphere, then we would have to import them, which is mind-bogglingly difficult. We would need to bring gases from elsewhere in the solar system, perhaps mining the atmospheres of Venus or the ice-rich moons of the outer planets, and transporting them to Mars. This is technically far beyond our current capabilities and might remain so for centuries. Even if we could thicken the atmosphere, we would face the problem of composition. Plants could, over time, convert carbon dioxide into oxygen through photosynthesis, but this would take an extremely long time, possibly thousands of years, even with genetically engineered plants or algae that are optimized for the task. And we would need nitrogen, which is essential for a breathable atmosphere and for plant growth. Mars has some nitrogen in its atmosphere and soil, but not nearly as much as Earth. Again, importing nitrogen would be necessary, adding to the immense difficulty. And then there is the problem of Mars's lack of a magnetic field. Earth's magnetic field protects our atmosphere from being stripped away by the solar wind. Mars lost its magnetic field billions of years ago. Even if we could create a thick atmosphere on Mars, it would slowly be lost to space over time. One proposed solution is to create an artificial magnetic field, perhaps by placing a large magnetic shield at the L1 Lagrange point between Mars and the Sun, which would deflect the solar wind and protect the atmosphere. This is a concept that sounds like science fiction, but it is within the realm of theoretical possibility. Warming Mars is another major challenge. Mars is cold because it is farther from the Sun than Earth, and because its thin atmosphere does not trap heat. To warm Mars, we would need to increase the greenhouse effect, trapping more solar heat. This could be done by releasing greenhouse gases such as perfluorocarbons, which are extremely effective at trapping heat. Factories on Mars could produce these gases and release them into the atmosphere. Alternatively, we could increase the amount of sunlight reaching Mars by using mirrors in space to reflect additional sunlight onto the planet. If we could warm Mars enough, the polar ice caps would begin to melt, and water would flow across the surface, creating rivers and perhaps even oceans. This would be a dramatic transformation, turning Mars from a desert into a world with a hydrological cycle. But even this would be a multi-century project. Introducing life to Mars would be a key part of terraforming. Plants, algae, and bacteria could be genetically engineered to survive Martian conditions and to help produce oxygen and build up the soil. These organisms would be the first colonists, the pioneers that would make Mars habitable for other life, including, eventually, humans. But this raises profound ethical questions. Do we have the right to introduce Earth life to Mars? What if there is indigenous Martian life, microscopic organisms that have survived in subsurface water or ice? Would we be committing a form of biological imperialism or even genocide by overwhelming native Martian life with Earth life? These are not just hypothetical questions. They go to the heart of our relationship with the cosmos, our responsibilities to other worlds, and our humility in the face of the unknown. Even if terraforming Mars is technically possible, it raises deep, ethical, philosophical, and practical questions. Should we do it? Is it our right to fundamentally alter an entire planet? Mars is a world with its own history, its own geology, its own story that has been unfolding for billions of years. Does humanity have the moral authority to rewrite that story, to erase Mars as it is, and replace it with Mars as we want it to be? Some argue that terraforming is our destiny, that it is the next step in human evolution, that expanding life throughout the solar system is a moral good. They argue that Mars is currently lifeless and barren, and that making it habitable for life, for Earth life, is an improvement, a beautification, a fulfillment of potential. Others argue that Mars should be preserved in its natural state, that it has intrinsic value as it is, that we should study it, explore it, perhaps even live on it in habitats, but that we should not fundamentally alter it. They argue that terraforming is arrogance, a form of cosmic vandalism, and that we should respect Mars for what it is, not try to force it to be something it is not. There is no easy answer to these ethical questions. They are questions that humanity will need to grapple with, that will require dialogue, debate, and ultimately decisions about our values and our vision for the future. In practical terms, terraforming Mars is not something that will happen in our lifetimes, or even in the lifetimes of our grandchildren. It is a project that would take centuries, require the cooperation of all of humanity, and cost resources on a scale we can barely imagine. It is a goal so distant that it might seem like fantasy, but it is also a vision, a dream, a statement of ambition. It represents the idea that humanity's future is not limited to one planet, that we can shape worlds, that we can extend the domain of life beyond its birthplace. Whether or not we ever terraform Mars, the very act of considering it, of exploring the possibilities, forces us to think deeply about who we are, what we value, and what kind of future we want to create. And that, in itself, has value. Chapter 9. The Economics and Politics of Mars. Who owns the Red Planet? Making Mars our home is not just a scientific and technical challenge, it is also an economic and political challenge. Who will pay for it? Who will govern it? Who owns Mars? These are questions that humanity will need to answer as we move from the dream of Mars to the reality of Mars. The cost of sending humans to Mars is staggering. NASA's estimates for a crewed Mars mission range from hundreds of billions to over $1 trillion, depending on the architecture and timeline. This is a sum that dwarfs most national budgets. For comparison, the Apollo program, which sent humans to the Moon, cost about $280 billion in today's dollars, and that was for missions lasting only a few days to a destination only 3 days away. Mars is orders of magnitude more difficult. Who can afford this? Currently, the only entities with the resources to fund a Mars mission are large governments and potentially very wealthy private companies. NASA, the space agencies of China, Europe, Russia, India, and others, all have Mars ambitions. SpaceX, led by Elon Musk, has made Mars colonization a central part of its mission, and is developing the Starship vehicle explicitly for that purpose. But even SpaceX's resources are limited, and the company relies on government contracts and private investment to fund its operations. This leads to a fundamental question. Will Mars colonization be a public endeavour, led by governments, or a private endeavour, led by corporations and wealthy. Individuals? The answer is likely a mix of both. Governments have the resources, the stability, and the long-term planning capabilities needed for such a massive undertaking, but governments are also subject to political pressures, changing administrations, and competing priorities. A Mars program that takes decades or centuries to complete will span many political cycles, and its funding is always at risk. Private companies, on the other hand, can move faster, take bigger risks, and innovate more freely than government bureaucracies. But they also need to be profitable, or at least have a path to profitability, which raises the question, what is the economic case for Mars? What value does Mars offer that could justify the enormous investment? The most commonly cited economic justifications for Mars include scientific knowledge. Mars offers answers to profound questions about the history of the solar system, the potential for life beyond Earth, and the processes that shape planets. This knowledge has intrinsic value and could also lead to practical applications. Resource extraction. Mars has resources, including water, minerals, and potentially rare elements that could be valuable. However, transporting material from Mars to Earth is currently prohibitively expensive, so any resources extracted on Mars would most likely be used on Mars or in space, not shipped back to Earth. A backup for humanity. This is perhaps the strongest argument. If something catastrophic happens to Earth, a self-sufficient settlement on Mars could ensure the survival of the human species. This is essentially insurance, and like all insurance, it is expensive and you hope you never need it. But many people, including notable scientists and entrepreneurs, believe this insurance is worth the cost. Inspiration and aspiration. A Mars program could inspire generations, drive technological innovation, and unite humanity around a common goal. The Apollo program had similar effects, leading to advances in computing, material science, telecommunications, and many other fields. A Mars program could do the same. However, none of these justifications guarantee economic profitability in a traditional sense. Mars is not a gold mine that will pay for itself quickly. It is a long-term investment with uncertain returns. This means that, at least initially, Mars colonization will require philanthropic funding, government support, or a very long-term vision from private investors. The political questions are equally complex. Who governs Mars? The Outer Space Treaty of 1967, which has been signed by over 100 countries, states that outer space, including the Moon and other celestial bodies, is the province of all mankind and cannot be claimed by any nation. This means that no country can claim sovereignty over Mars. But the treaty was written in the context of Cold War competition and the race to the Moon, and it is unclear how it applies to permanent settlements and resource extraction. If a company builds a habitat on Mars, who has jurisdiction over it? If a person commits a crime on Mars, what law applies and which court has authority? If resources are extracted on Mars, who owns them? These are questions without clear answers. Some argue for a new international treaty, a Mars Treaty, that would establish clear rules for governance, resource use, and legal frameworks. Others argue for a more decentralized approach, where settlements are self-governing and disputes are resolved through negotiation and arbitration. Still others suggest that Mars should be considered a new frontier, where the first settlers establish their own rules and governance structures, similar to the American Wild West or the early colonies in Australia and the Americas. There is also the question of representation. If Mars develops a significant population, should they have representation in Earth's governments? Or should Mars have its own government? At what point does a Martian settlement become a Martian nation? These questions will become increasingly urgent as the population on Mars grows, and as the people there begin to develop their own identity and interests, which may diverge from those of Earth. And there is the question of equity. Space exploration has historically been the domain of wealthy nations. Will Mars colonization follow the same pattern, with only the rich and powerful having access? Or can Mars be a place of opportunity for all of humanity? How do we ensure that Mars does not become a playground for billionaires or a military outpost for superpowers, but a place that benefits all of humanity? These are difficult questions with no easy answers. They will require negotiation, compromise, and a willingness to think beyond national interests and short-term gains. They will require us to develop new forms of governance, new legal frameworks, and new ethical guidelines for how humans interact with other worlds. but they are also exciting questions, because they force us to imagine new possibilities, new forms of society, new ways of organising ourselves. Mars could be an opportunity to start fresh, to build a society based on lessons learned from Earth's history, to create a culture that is more equitable, more sustainable, more thoughtful. Or it could replicate the same patterns of inequality, conflict and exploitation that have characterized human history. The choice is ours. The economics and politics of Mars are not just about money and power. They're about our values, our priorities, and our vision for the future. They're about deciding what kind of species we want to be, what kind of legacy we want to leave, and what kind of relationship we want to have with the cosmos. Chapter 10. The Meaning of Home. Why Mars Matters. We have journeyed through the science, the technology, the challenges, and the possibilities of making Mars our home. We have explored the planet itself, the journey to reach it, the means to survive there, the potential to thrive, and even the dream of transforming it. But now, as we near the end of this long contemplation, we must return to the question that started our journey. What does it mean for Mars to be our home, and why does it matter? Home is more than a place. It is a feeling, a sense of belonging, a connection to the land and the community around you. Home is where you are safe, where you are known, where your memories are made. Home is the place you return to, the place you defend, the place you improve for future generations. Can Mars ever be that? Can a cold, barren, hostile world become home in this deep, emotional sense? The answer is, not yet. For us today, Mars is a destination, a goal, a vision. It is a point of light in the night sky, a world we have only explored with robots. It is a place that exists more in our imaginations and our plans than in our lived experience. For Mars to become home, people must live there, not just for months but for years, for decades, for lifetimes. They must build communities, raise families, create culture. They must adapt to the Martian environment, and the Martian environment must, in small ways, adapt to them. They must develop a sense of place, a feeling that Mars is not just where they live, but who they are. This transformation, from Earth humans to Martians, will take time. The first generation on Mars will always think of themselves as expatriates, as people from Earth who happen to live on Mars. But their children, born under a butterscotch sky, growing up in habitats and greenhouses, learning to walk in low gravity, seeing Earth as a distant blue star, they will be different. They will be Martians, and for them, Mars will be home in a way it never can be for us. But this raises a profound question. What is our obligation to these future Martians? If we set in motion the colonization of Mars, we are making a decision that will affect people who have not yet been born, people who will live on a world we have chosen for them. We are deciding that human life will extend beyond Earth, that the human story will be written on multiple worlds. This is a momentous decision, perhaps the most momentous our species will ever make. It is a decision that should be made thoughtfully, carefully, with humility and wisdom. So why should we do it? Why should we invest the resources, take the risks, face the ethical dilemmas, and commit to a project that will take centuries to complete? There are many answers, and each person will weigh them differently. One answer is survival. Earth is fragile. We are increasingly aware of the threats, both natural and self-inflicted, that could end or drastically reduce human civilization. Asteroids, supervolcanoes, pandemics, nuclear war, climate change, all pose existential risks. A self-sufficient settlement on Mars would be insurance against these risks. If Earth suffers a catastrophe, humanity would survive on Mars. This is a powerful argument, one rooted in the basic instinct for self-preservation. But it is also a sobering one, because it acknowledges the fragility of our current existence. Another answer is knowledge. Mars holds answers to profound questions. Did life ever exist on Mars? If so, what happened to it? How do planets form and evolve? What conditions are necessary for life? These are not just academic questions. They are fundamental questions about our place in the universe, about the nature of life, about the possibility of other civilizations. By exploring Mars, by studying it, by attempting to live there, we learn not just about Mars, but about Earth, about life, about ourselves. A third answer is inspiration. The Apollo moon landings inspired a generation. They showed that humans could do seemingly impossible things, that we could reach beyond our planet, that the future was not just a continuation of the past, but something new and exciting. A Mars program could have a similar effect. It could inspire young people to pursue careers in science, technology, engineering, and mathematics. It could drive innovation, leading to new technologies that improve life on Earth. It could unite humanity around a common goal, fostering cooperation and reducing conflict. A fourth answer is destiny. Many people believe that humanity is meant to explore, to expand, to spread throughout the cosmos. They see the colonization of Mars as the next step in a journey that began when our ancestors left Africa, that continued when we crossed oceans and settled continents, and that now extends into space. They see it as our nature, our purpose, perhaps even our obligation. We are the universe's way of knowing itself, the cosmos becoming conscious, and with that consciousness comes a responsibility to extend life, to protect it, to spread it. And there is a fifth answer, one that is harder to articulate but perhaps the most important: wonder. The universe is vast, mysterious, and beautiful. Mars is a world, a real place, that we can reach, explore, and perhaps inhabit. The idea of humans living on Mars, of looking up at Earth from another planet, of building a new branch of human civilization on a new world, is awe-inspiring. It speaks to something deep in the human spirit, a longing for the extraordinary, a desire to be part of something larger than ourselves, a need to push boundaries and see what lies beyond. This wonder, this sense of possibility, is part of what makes us human, and it is perhaps reason enough. But we must also acknowledge the arguments against Mars colonization. Some argue that the resources should be spent on solving problems on Earth, that we should fix our own planet before we try to inhabit another. There is merit to this argument. Earth faces serious challenges: poverty, inequality, environmental degradation, political instability. Billions of dollars spent on Mars could also be spent on clean energy, education, healthcare, or conservation. And it is true that we should not abandon Earth. Earth is our home, our mother world, the only place in the universe known to harbour life. We have a moral obligation to protect it, to care for it, to ensure it remains habitable for future generations. But this is not an either-or proposition. We can work on Earth's problems and explore space. In fact, the technologies developed for space exploration often have applications on Earth. Solar panels, water purification systems, closed-loop life support, all have terrestrial uses. More importantly, the perspective gained from seeing Earth from space, from understanding its fragility and uniqueness, often leads to a greater appreciation for our planet and a greater commitment to protecting it. The famous blue marble photograph of Earth, taken by Apollo astronauts, is credited with helping to launch the environmental movement. A view of Earth from Mars could have a similar effect, reminding us of how precious and rare our home is. Ultimately, the decision to make Mars our home is not just a technical or economic one. It is a moral and philosophical one. It is about what kind of future we want to create, what kind of species we want to be, and what kind of legacy we want to leave. Do we want to be the species that stayed on one planet, or the species that reached for the stars? Do we want to be defined by our limitations or by our ambitions? Do we want to play it safe, or take the risk and see what we can achieve? There is no right answer, no single correct path forward. But there is value in asking the question, in exploring the possibilities, in dreaming big. And there is value in taking the first steps, even if the destination is far away and uncertain. Every great journey begins with a single step, and that step is often the hardest. But it is also the most important, because it is the step that commits us to the journey, that sets us on the path, that transforms the dream into reality. Mars calls to us. It has called to us for centuries, a red beacon in the night sky, a mystery, a challenge, a promise. We are closer now than we have ever been to answering that call, to reaching out and touching another world, to planting the seeds of a new branch of humanity on an alien soil. Whether we succeed, whether Mars truly becomes our home, is not yet determined. It depends on our choices, our efforts, our wisdom, and our courage. But one thing is certain: the journey has begun. Rovers crawl across the Martian surface. Orbiters map the planet in unprecedented detail. Rockets are being designed and tested. Plans are being made. People are training. The first steps have been taken. And with each step, Mars becomes a little less alien, a little more familiar, a little closer to being home. This is the journey we are on. It is a journey of science and engineering, of courage and sacrifice, of dreams and determination. It is a journey that will test us, that will change us, that will define us. It is a journey to Mars, yes, but it is also a journey into our own potential, into the question of what humanity can achieve when we dare to reach beyond our current limits. The future is not yet written. Mars is not yet home, but it could be. And that possibility, that glimmer of hope on a distant horizon, is worth reaching for. It is worth the effort, worth the cost, worth the risk. Because in reaching for Mars, we reach for something greater than ourselves. We reach for the stars, for the future, for the very essence of what it means to be human. And in that reaching, we find meaning, we find purpose, we find home, not just on Mars, but in the journey itself, in the act of exploration, in the courage to dream and the determination to make those dreams real. Mars is calling. And we, the children of Earth, the descendants of those who first looked up at the night sky and wondered, we are ready to answer. The journey to Mars is the journey home, to a home that does not yet exist but that we will create together, one step at a time, across the vast and silent void to a red world waiting to be born anew.